Hi, everyone. I have in front of me pretty much all the problems, at least all the odd numbered problems from section 11.7 in the Stewart textbook. This is the section for testing series, and they don't give you any hints about which convergence test to use. We've seen a bunch, right? We started out with stuff like P-series, geometric series. Those tended to be not so bad. Then we learned about the integral test, which, I mean, you have to recall everything you know about integration, so that's kind of a beast. Then you have the direct and limit comparison tests, which can be kind of tricky on their own. And I guess more recently, ratio and root test, alternating series test. That's all I can think of. But yeah, lots of tests for whether a series converges or not. And all these problems that I have written down, yeah, we're going to just try to come up with the best approach for each of them. I recommend you attempt these problems first before watching the video, or at the very least, watch the video, but pause it whenever I get to a new problem, and attempt the problem for yourself. Give it at least, a few minutes, try a couple different convergence tests. If you get stuck, that's totally fine. Some of these are going to be difficult. But do attempt it first yourself, and then watch me try to tackle it. Because this is the sort of thing where you really have to learn by doing, and it's only the helpfulness of watching somebody else do it is pretty limited. But this will at least be a sort of study guide to guide you in your solutions once you've attempted them yourself. So okay, I look at 1A. 1A is we should recognize that immediately as a geometric series, and if you don't see it immediately, then try rewriting the terms as 1/5 to the n. Then we know that this converges because 1/5 is between -1 and 1. So this is, yeah, literally a geometric series with the right value of r, basically. Part B looks very similar. It is the same series, but I'm adding n to the denominator. So I think to myself, okay, I could probably compare to the series I just worked on in part A. In particular, n is a positive number. It's between 1 and it just keeps increasing from there. So I'm adding something positive to the denominator. That makes it bigger, which makes the whole fraction smaller than the fraction in part A. So in particular, it's smaller than 1/5 to the n. Bigger denominator makes a smaller fraction. And so that implies our series, the one we're given, actually converges by direct comparison to the one before. Right, it's less than a geometric series which converged. If you're less than a convergent thing, you converge. 3A, I have a 3 to the n in the denominator. That's growing extraordinarily quickly as n increases, whereas the numerator is growing. I mean, it is growing. It's growing kind of slowly, I would say. So I would expect this to converge. Maybe, we just use the comparison test. Maybe I think, oh, could I compare this to anything? But not exactly. I would want this to be less than some really nice convergent series. And that's sort of hard to do. It's not going to be less than 1/3 to the n, for example, because that n is growing. So maybe direct comparison isn't going to work. I might try like a limit comparison, or I might try like a ratio test, right? So I see a power of n. I know that in a ratio test, a lot of terms tend to cancel. So maybe that'll help me. So I think, so ratio test says I want to look at the n plus first term, which is going to be n plus 1/3 to the n plus 1, and multiply, well, divide by the nth term, which should be the same as multiplying by the reciprocal here. So 3 to the n over n instead of n/3 to the n. And we do indeed get a lot of cancellation, right? The 3 to the n and the 3 to the n plus 1 leave behind a single 3 in the denominator. So this limit, I can actually drop the absolute values on this limit because everything's positive. So I should just be left with n plus 1 over 3n, right? 3 coming from, that was the only 3 left, and then the other terms just stuck around. And then in the limit, this is 1/3. And then you have to keep in mind what the conclusion of the ratio test is. It says if this is less than 1, then that implies, well, really it implies your series converges absolutely. But in this section, we're just talking about standard convergence. So yeah, absolute convergence implies convergence. So we're good to go. And I'll just write here, that was the ratio test. Part B is the same as part A, but it's flipped. So, okay, if part A converged, I would expect part B to diverge. And if I'm thinking it's going to diverge, maybe the first thing I do is I just apply the divergence test. And okay, I look at this, I say as n is going to infinity, each of those, the numerator and the denominator, are both going to infinity. So it's sort of in an indeterminate form. And whenever I see a limit where I get an indeterminate form, I think L'Hopital's rule. So I take a derivative of top and bottom. On the bottom, you'll just get 1, so that's nice. On the top, the derivative of 3 to the n, maybe you forget this, it's natural log of 3 times 3 to the n. It's the same as e to the n, but you have to add that correction factor. Since the base isn't e, it's 3. But whatever it is, you still get a 3 to the n on top. That part's going to infinity. The bottom is fixed now, so this goes to infinity. And by the divergence test, we do in fact find that the series diverges, right? Because the divergence test says if the terms go to anything except for 0, you automatically get divergence. Okay, scrolling down, 5a looks like n over n squared plus 1. I think to myself, the only terms that should matter are the highest powers in the top and bottom. Right, the plus 1 shouldn't impact us too much. So I think n over n squared is like 1 over n. So potentially this is like a harmonic series. So I ask myself, can I compare to the harmonic series directly? If so, what I would want to happen is I would want our terms to be bigger than or equal to the harmonic terms. Because if you're bigger than a divergent thing, you're divergent. So I'll put a question mark here. That's what I want. Is it true? No. Right. The denominator on the left is bigger. I'm adding 1 to it, so the fraction's smaller. So we can't do a direct comparison. But if your direct comparison fails, you probably want to try limit comparison. So we're doing limit comparison between our series and the harmonic series. So let's just do some algebra before evaluating this limit. This multiplied by the reciprocal, you'll get an n squared on top, still with an n squared plus 1 on bottom. And then that limit is 1. And the limit comparison test says that anytime you get something that's a positive finite number, in this case 1 is positive and finite, then your series behaves the same as the original series. So this was my series. The series I'm comparing to was harmonic, so they behave the same. We know harmonic diverges, so I get diverges for this one by limit comparison. Cool. Part B is the same thing, but you raise it to the nth power. And if I see an nth power, I immediately think root test. Root test looks like this. You take your terms, you put them inside an absolute value, which in this case isn't going to matter. Everything's positive anyway, but let's just write it to be precise. And then you take the nth root, then you take the limit, you see what happens. we get limit as n goes to infinity. The exponent that everything's being raised to, that nth power, will get canceled out by the nth root. And like I said, the absolute values don't matter. So you're just looking at this. That limit is 1. And, sorry, slight typo. I forgot my n squared. 1 would have been a bad thing, but we're not actually going to get 1. So this is n squared plus 1 in the denominator. I just miswrote it. I didn't pay attention closely enough. So I take the limit, and now it's indeterminate. I apply L'Hopital. This will be a good thing. Derivative of the top is 1. Derivative of the bottom is 2n. As n goes to infinity, that fraction goes to 0. That's less than 1, which implies convergence by the root test. Cool. 7 is interesting. 7 sort of has 2 parts to it. You have this 1 over n and this 1 over n factorial. And the question is, which one's more important? If you focus on the 1 over n, then maybe you think, ooh, this is like a harmonic series. Maybe it diverges. If you focus on the 1 over n factorial is growing insanely fast. So that series on its own would converge. And so the question is, combining them, what do I get? And after staring at it for a while, you might come to the conclusion that, well, if I focus on 1 over n factorial, and I'm adding something positive to the denominator, then the denominator is bigger, which makes the whole fraction smaller. So actually, you can get away with a direct comparison here. This is smaller than, again, I could write strictly smaller than if you want, but it doesn't make much of a difference. Strictly smaller than 1 over n factorial as a series. And we know that that converges. So if you're smaller than something that converges, you converge as well. This is direct comparison. If you don't realize why 1 over n factorial converges, not sure if there's an easier way to show it, but you could do something with a like a Taylor series here. There's a Taylor series for e to the x that looks like x to the n over n factorial. And so, I mean, if you know that, which maybe you don't, but whatever, if you know that, then plug in 1 for plug in 1 for x, and this actually, 1 to the n becomes 1, so you get this series. So you get an actual value for this series. This series is exactly equal to e, which is not infinity, so it converges. I guess our series is very slightly different. It starts at a different value, but that doesn't make a difference in the convergence. Okay, either way, the direct comparison works. Part B looks pretty similar. We have, again, 1 over n and 1 over n factorial, but this time we're adding those 2 fractions. And in this case, let's see. Yeah, in this case, this is now bigger than the series, the harmonic series. Why? Well, the series on the left, this term is positive. So yeah, I mean, adding something positive makes the left bigger than the right. And we know that the harmonic series diverges, so this one diverges as well. Again, direct comparison test. Okay. Let's see, number 9. 9 again strikes me as something that is close to a harmonic series. Let's see how I could write it out. Let's stare at it for a second, ask ourselves if we can do a direct comparison. Probably not. If I wanted to directly compare to the harmonic series, 1 over n, I would want the series on the left to be bigger, but this -1 kind of makes it smaller. The +1 on the bottom also makes it smaller. So I can't do a direct comparison. But anytime that fails and there's like an obvious candidate to compare to, you should try out limit comparison. In this case, our obvious candidate is harmonic. It's not obvious to you. Just think about forgetting about the constants, and then n squared over n cubed simplifies to 1 over n. So that's the frame of mind you should get into, is try to toss away confounding factors, right? Anything that makes it more complicated than it needs to be, and then ask what happens to the simplified version. In this case, the simplified version is harmonic, which diverges. Simplifying this fraction here, I get, let's see, the n comes up to the top. So instead of n squared minus 1, it's n cubed minus n. On the bottom, it's n cubed plus 1. Those are the same degree, right? They both have a third power. So that limit is 1, which is good, right? That's a positive finite number. So limit comparison test says the two series behave the same. In this case, the one we were comparing to was the harmonic series. So by limit comparison, ours diverges as well. And then number 11 is an alternating version of the same thing. Okay, so there's a chance this one could converge, even though the last one diverged. Because an alternating series has positive and negative terms that can tend to cancel out very nicely. If not fully cancel, at least they start to like balance out a little. So this could converge. Probably the best thing to do is the alternating series test, but the alternating series test has you check if these terms are decreasing, which is going to be a little finicky. So I mean, maybe you try a ratio test. I feel like it would be inconclusive. So yeah, let's try alternating series. So 1, you want to show that it's decreasing. And technically, all you really need to show is that it's eventually decreasing, meaning like maybe the terms start out going up, but as long as they eventually go down and keep going down forever and ever and ever, you can sort of just look at like this part, you can ignore the first part of the series and say, oh, it's starting at n equals 5 or something. My series is decreasing towards 0. And then by the alternating series test, that series starting at n equals 5 would converge. But then the series starting at n equals 1 must converge as well, because I mean there are finitely many terms in the beginning, so that's not going to affect it. So okay, talking about decreasing or eventually decreasing, typically a real nice way to do it is just think, what if you treated this as a function? So instead of n squared minus 1, it'll be x squared minus 1 over n cubed becomes x cubed plus 1. And then I want to take a derivative. So I need to remember quotient rule. This one's probably going to get ugly. Quotient rule, square the denominator. Then take the denominator and multiply by the derivative of the numerator. Minus, and then flip it. So numerator times derivative of denominator. You probably want to simplify this. I won't simplify the bottom because it's not going to matter. You'll see why in a second. What does the numerator simplify to? I have a 2x to the fourth minus a 3x to the fourth. So that's negative x to the fourth. I'm just going to do this in my head. Apologies. I have a 2x. I have a plus 3x squared. Okay, so we have that. Hopefully that's correct. And keep in mind, if you're talking about the function being decreasing, you want this to be less than 0. Right? Less than 0 means negative. Negative means the slope is negative, which means the function is going down, it's decreasing. But when is that fraction negative? Well, the denominator is positive, right? Anything squared is positive or a 0, but it's definitely not 0. So yeah, we're fine, right? That means I can just look at the numerator. So I can just ask, is the numerator less than 0? And I guess I could factor something out of the numerator. I could ask, pull a negative x out. I'm left with an x cubed minus 3x minus 2. I want to know if that's negative. Well, the only time the product of two numbers, in this case, these two numbers, is negative is if one's negative and one's positive. We know that negative x is negative because x is basically n, and n goes from 1 to infinity. So that guy's positive. That means we only care about if the term in parentheses is negative. Then I think I probably have to factor this guy to figure out if it's negative. Factoring cubics can be tough, but you can probably guess and check a bit. You could say, try plugging in 1 for x. That doesn't work. Plug in 2. Yeah, so if you plug in 2 everywhere x appears, then you get a true statement. Well, it would be true if it was an equality, right? So 8 minus 6 minus 2 is 0. So I know that x minus 2 is a factor. And then I guess I could find the other factors of this by doing long division of polynomials, which it's been a while. Put the x into x cubed, you get x squared, then multiply down, you get x cubed minus 2x squared. That's the term we're subtracting. So the x cubes go away, then I get a negative 2x squared. And I'll bring the 3x down. Put the x into that, you get, I guess I don't need to bring the 3x down. Anyway, put the x into that, you get a 2x. And multiply down, you get your 2x squared, you get minus 4x. That's the term we're subtracting. And then we keep in mind about this negative 3x. So that's negative 3x plus 4x. So that's just x. Then I put the x into that, I get a 1. X minus 2, I subtract that. And then again, keep in mind the minus 2. So that's x minus x is 0, negative 2 plus 2 is 0. You get no remainder, which is great to see. That means you can factor that cubic as that. So let's write that x squared plus 2x plus 1. Okay, this is x squared plus 2x plus 1. I want that to be negative, but I can factor it even further. This is x plus 1, the whole thing squared. And the only way that's going to be negative, well, look at this. This term's positive because it's squared, right? It's some positive thing squared, so it's positive. So the only way this product is negative is if the first term is negative, and that happens when x, let's see, is that right? Interesting. Let's see, that's not what I wanted to see. Did I make a misstep somewhere? Yeah, sorry. Okay, at the beginning, these should all be the opposite way. My bad. Okay, because in this first step, we pulled out the negative x, and then we said negative x is always negative. So we actually want, this to be, well, I guess this one's fine. You want that to be negative. That happens whenever this term is positive. So positive, positive, greater than 0 for all of these, then that becomes that. Okay, so I had the sign wrong. No big deal. As long as x is bigger than 2, it's decreasing. So like what's happening is here's 1, here's 2, here's 3. For the first few terms, it's increasing, but then past there, it decreases forever. So as long as I start my series at, say, 3, then I have a decreasing series, and we're good to go. So let's just write this, just to save room. This is less than 0 when x is greater than 2. That's what we just figured out. So it's eventually decreasing. So that checks off number 1. And number 2, you want to look at your limit. So the limit as n gets large of the non-alternating part of the series. And then, however you want to do this, a couple applications of L'Hopital's rule, or just say the bottom is a higher degree, so this has to go to 0. That checks out as well, right? That's the other thing we wanted. So you know that this is convergent by the alternating series test. Okay, so that one was pretty hard, honestly. You had to do some ugly quotient rule, ask when that numerator was negative. Even I made a little mistake along the way. So yeah, that's sort of mean. I don't know if there's a better way to tackle it, though. Anyway, let's look at 13. So number 13, I glance at that. I say e to the n is going to grow much faster than n squared. And if the numerator is growing faster, that means this should blow up, right? This should diverge. And the way you want to show it is just use the divergence test. Again, if you want to use L'Hopital's rule, go for it. Derivative of e to the n is e to the n. Derivative of n squared is 2n. That's still an indeterminate form. So you take another derivative, but e to the n still stays the same, and now that goes to infinity. So this is the series diverges by the divergence test. That's much quicker than the one before it. And then 15 looks scary. 1 over n square root log n. The question is, like, is this term winning? Is the 1 over n, the harmonic component of this series, going to make the difference between converging and diverging? Because, I mean, you could make the argument that you're multiplying the denominator by like some positive thing. So maybe it converges, or maybe it, maybe the terms are smaller than the harmonic series. In fact, they are. But being smaller than a divergent thing doesn't mean you're necessarily convergent, right? You have to be like significantly smaller. And square root of log n grows pretty slowly. So I don't know, I guess we'd have to come up with a good test. Looks like we can't do a comparison based on what I was just saying. We can't do ratio test or root test. Those would be hideous. Doesn't have an alternating component. The only thing I can think to be left with is the integral test, which we haven't seen yet, so might be a good one to try out. Again, try this out yourself before seeing me do it. Maybe you tried some comparison tests on your own and failed, and now you have the suggestion to do integral test. I'm going to say pause the video and try again, because this is a good one to review. But okay, here we go. Rewrite the improper integral as we always would. Sorry, this is supposed to be a t going to infinity, so that upper bound is getting arbitrarily large. And then this is same integrand. Now the question becomes, how do I integrate this thing? What you might come to is like, ooh, this natural log is nice. If I make a u substitution and pick that as u, then 1 over x dx is du. So this looks like 1 over the square root of u du. So let's write that down. Again, we're still going to have to keep this limit out here. But this is 1 over the square root of u, that's u to the negative 1/2 du. Because we chose u to the log x, so du was 1 over x dx. Okay, I didn't write my bounds on here, but I should. Note that I made a substitution. So before my bounds were in terms of x, I want them now to be in terms of u, but u is just the natural log of x. So if I started with 2, the new bound is natural log of 2. I started with t in the world of x's, that's natural log of t when you convert it to u, just by plugging into this guy. Okay, now we evaluate this integral. U to the negative 1/2, when I integrate, becomes u to the 1/2 over 1/2. Dividing by 1/2 is the same as multiplying by 2, and then u to the 1/2 is the square root. So we have this from natural log of 2 to natural log of t. I guess I could pull that 2 out just to make our lives easier. And then plugging in my bounds, I get square root of natural log of t minus square root natural log of 2. And okay, we don't have to be super careful here. We just have to focus on this part. As t gets big, natural log gets big. And even though it's in a square root, the square root's also going to infinity. So this goes to infinity, which means the integral diverges. And now we just have to check, was this a valid comparison to make? It's not always true that a series and its integral companion behave the same way. So you have to actually test like 3 assumptions. So our 3 assumptions are, 1, you have to check that your terms are, well, the function is continuous. That one's basically a freebie. I don't think we will ever see a non-continuous function in this class. The other one is positive. You have to have positive terms, but you do. N is positive, right? Because it starts at 2. Natural log of 2 is positive, and the square root of a positive number is positive. So that's fine. Positive is correct. The only time natural log could be negative is if n is less than 1. So that doesn't happen for us. And then you have to check that it's decreasing. This is usually the one that requires a bit of work. I think I'll use some high-powered tools. Instead of taking a derivative and showing it's negative, or showing that like the next term in the sequence is smaller than the previous term, I'll use a nice high-powered tool. So I'll say decreasing because n square root log n is increasing. But then you ask, how do I know that? And I know that because n square root of n and log n are increasing. Right, just graph them. N is a line with positive slope. Square root of n always goes up, log n always goes up. So those are all increasing. And the product of positive increasing functions is increasing. So yeah, going backwards, these are increasing, so their product is increasing. Also, their composition, right, the square root of the log will be increasing. And since that's increasing, when I take the reciprocal, 1 over that should be decreasing. Again, because it's positive, you're allowed to do that. So a lot of weird rules there, but that checks out. And so we get that R series converges by the integral test. So you can be sort of hand wavy on these things, but you do have to check them. Because those 3 things confirm that, you know, whatever happens to the integral happens to the series. Okay, so in that case, we're good. Next set of problems. 17 is a fun one. 17 is one that you can actually evaluate, weirdly. I could say this is actually cosine of pi. Cosine of pi is -1. So this series, if you were to add up all infinitely many terms, actually does give you -1. And that's a finite number, so this thing converges. But you really only know that if you know the Maclaurin series, or if you know the Maclaurin series for cosine. The Taylor series about x equals 0 for cosine looks like this. It's x to the 2n over 2n factorial. So the only difference between these guys is, you know, I have a pi thrown in for the x. So that's where that comes from. But I don't think you're expected to know that by this point in the chapter. So what's an alternative way to figure out that this is convergent besides just finding the sum? This looks like a prime time to do ratio test. Ratio test says, okay, look at your n plus first term, and you got to be careful. Plug in n plus 1, but do it with parentheses around the n plus 1. So that'll be 2 times the quantity n plus 1 is 2n plus 2. Same story in the denominator. That's 2n plus 2 factorial. And then multiply by the reciprocal of what you started with. Okay, the absolute value bars are going to make no difference here because everything, well, I mean, they are making a difference. I guess I should have been a little careful here. And when I wrote this out, oops, done something like, you know, don't forget about the -1. Right? This guy would have been -1 to the n plus 1. And then you would have divided by -1 to the n, which is the same as multiplying by -1 to the n. So if you want to be precise, you can, but once you take the absolute value, those guys get eliminated because they're either plus or -1. So they're not going to impact us. So let's just write this as pi to the 2n plus 2. And let's put similar terms over similar terms, right? So group these two together, and then group those two together. So this will be over pi to the 2n. You'll get some good cancellation there. And this is 2n factorial over 2n plus 2 factorial. And I'll go ahead and write this in an even nicer way. So on top, keep it the same. On bottom, 2n plus 2 factorial is 2n plus 2 times 2n plus 1 times 2n times 2n minus 1 times 2n minus 2. Keep going down. If I keep going down, that's basically just a fancy way of saying 2n factorial, and then those cancel. Right? So cancellation here, cancellation here gives me, I guess I'll keep those. That gives me the limit as n goes to infinity of pi squared on top. I need to leave enough room for the denominator. That's if I FOIL it out, 4n squared plus 6n, I guess, plus 2. But whatever it is on bottom, it's some quadratic with n in it. That's going to go to, the denominator is going to go to infinity, which means the whole fraction should go to 0 because the top is just a constant. So ratio test says if this is less than 1, then your series converges absolutely, which means it converges by the ratio test. Right, number 19. 19 is the sum of two really nice individual terms. It's not often you see two things summed together like this, but when you do, you probably want to ask the question, do they converge on their own? And in this case, the answer is yes. 1 over n cubed is a p-series with p greater than 1, so that converges. 1 over 3 to the n is 1/3 to the n, which is a geometric series with common ratio between -1 and 1, so that converges. And you know that whenever you have two convergent series, you can either break them apart or add them together and it doesn't change anything. So, right, this. And we just said each of these converged. Right, like this though. So this converges, right? If you sum two convergent things, that's saying each one of those series sums to some finite number. And the sum of two finite numbers is also a finite number. So it converges by p-series and geometric series. Okay, number 21. Looks like a prime candidate for another ratio test. I think that whenever I see n factorial, right, maybe you think of root test when you see the nth power, but really root test is only useful if everything is raised to the nth power. In this case, we have some confounding terms, but ratio test also works good on nth powers. So let's see what that looks like. Limit as n goes to infinity, absolute value. Look at your n plus first term. And then look at the reciprocal of what was given to you. So this is n factorial on top, 3 to the n times n squared on bottom. In this case, there's no negative terms, so the absolute value doesn't matter. And if we look at cancellation, this will be an interesting one. I mean, the 3n and most of the 3's on top cancel. So at the very least, I have, drop the absolute values. I have a 3 n plus 1 squared n factorial over, okay, n plus 1 factorial is n plus 1 times n factorial. So you get more cancellation. Oh, and in fact, even more cancellation, because one of these guys will cancel out with the n plus 1 on bottom. Hoping let's see, I forgot an n squared as well. Right, there's an n squared hiding here that I neglected, so there's still an n squared on the bottom. But there we go, that's still nice, right? So that's the limit as n goes to infinity. 3 times n plus 1 over n squared. The bottom blows up faster because it's a higher power of n, so this goes to 0. Again, that's good to see. That gives us convergence. Again, the ratio test being used. And as long as it's not 1, as long as your limit isn't 1, you get some nice conclusion. In this case, convergence, or absolute convergence, if you want to write that. Okay, next set. 23, okay, I was just talking about the root test, and I said if everything is to the nth power, you should think of root test. I don't know why they've changed their indexing and made it k this time, but the principle still holds. Everything is, well, everything is not raised to the kth power, but you should still think to use root test. But, you know, it would be a lot better if this was 2 to the k, if this was 3 to the k. Okay, the bottom is fine already, since it's already a kth power. But I can't just write that. I can't just write, okay, the series on the left is equal to the series on the right. That's definitely not true. I want this to be 2k minus 1. So, okay, I mean, why not just multiply by a half? Put a 1/2 out front, then 1/2 times 2 to the k is, the same as 2 to the k over 2. So that's 1 less 2, that's 2 to the k minus 1. And if I want 3 to the k plus 1, well, why not just multiply everything by 3? Because then that would be 3 times 3 to the k, which is 3 to the k plus 1. Okay, and then putting both of those two things together, I want to multiply by 3. I also want to divide by 2. So just put a 3/2 out front. Now you know that whether or not this series converges, this series is exactly equivalent to whether or not the series in the highlighted region converges. Right? The 3/2 won't make a difference. If you take a convergent series and multiply it by a constant, there's no way you get infinity. Right? A finite number times a finite number is a finite number. So the 3/2 basically doesn't matter. And so we say, okay, let's do the root test. This is k goes to infinity. And I just take the kth root of everything, focusing on these. So that'll just be 2 times 3 over k, right? Because the kth root eliminates the kth powers. And this is definitely 0. 0 is less than 1. Right? It's the same sort of conclusion as the ratio test. Less than 1 means you converge, in this case by the root test, because that 3/2 doesn't matter. All right, 25 tends to stump people. Usually what I recommend is like write out what the terms look like, but that takes a while and I don't want to waste more time. So what I'm going to say is this is really amenable to ratio test. So ratio test looks like this. It's going to take up a lot of space. Okay. In the numerator, I'm always multiplying all odd numbers together. 1 times 3 times 5 times 7 times ... times 2n minus 1. But keep in mind, I'm trying to write down the n plus first term this time. So if I plug in n plus 1 for n, that becomes 2 times the quantity n plus 1. That's 2n plus 2 minus 1. So that's my last term should actually be 2n plus 1. Okay, but it did have all the preceding terms before it, so it's important that I write those. Similar logic for the denominator. I keep going. Eventually, I hit 3n minus 1. And then my next term will be 3 times the quantity n plus 1. It's 3n plus 3. Minus 1, which is 3n plus 2. Okay, so that's, right, this whole thing is my a sub n plus 1 term. And then what's going to go here is the reciprocal of an. That'll give me an plus 1 over an. And then I take my limit. That's the ratio test. So, okay, reciprocal, let's just write it down. 258 ... 3n minus 1. Numerator becomes the denominator, ... 2n minus 1. And now hopefully you see 1 cancels with 1, 3 with 3, 5 with 5, 2n minus 1 with 2n minus 1. 2 cancels with 2, 5 with 5, 8 with 8, 3n minus 1 with 3n minus 1. And you're just left with these final terms. So we're taking a limit of that, but that is something very nice. That gives you 2/3. Again, compare it to 1. 2/3 is less than 1. So let's write this down here. That implies converges by the ratio test. Okay, so it's an exceptionally weird looking series, but it can be handled with standard techniques. The next one is also a bit weird looking. 27. Alternating series, right? ln over root n is always positive. So this is a classic form for alternating series. So I think to myself, maybe I should just do the alternating series test. And again, we have to be careful. We want to show that it's decreasing. But it's fine if it's not decreasing to begin with, as long as it's eventually decreasing. So, okay, we set up a function to represent this. So it'd be natural log of x over square root of x. We take the derivative and see if it's negative. So the derivative, again, you got to do a little quotient rule. Squaring the bottom gives me x, and then it's bottom times derivative of the top minus top times derivative of bottom. Okay, derivative of square root is 1 over 2 square root of x. Okay, so that's the that's the condition we're in. It's not the nicest expression I've ever seen. Let's focus on the numerator. Square root of x times 1 over x. Well, x is root x times itself. So I guess one of the root x's cancel, and you're left with 1 over root x. And then here, I guess I could put the natural log up top. You can even put the 2 up top. Well, anyway, I'll do that in a second. Natural log of x over 2 root x. So if I want to combine those two fractions, get a common denominator, I think I can write this as 1 minus a half log x with square root of x in the bottom. And then let's also keep our x down here. Okay, so fingers crossed that my algebra is all correct. Where do we go from here? Well, same as last time we did the alternating series, we're asking when this derivative is negative. So when is it less than 0? Well, it's less than 0 when the numerator is less than 0, because the denominator is always positive, so we don't have to worry about that. So I'm asking when this is true, but I can just rearrange that. That's when it's the same as saying 1/2 natural log has to be greater than 1. Multiplying by 2 gives me this. Exponentiating both sides, so raising each side, like doing e to the power of each side, I get x is greater than e squared. I forget what e squared is. E is 2.718 roughly. So, okay, that's 7.3-ish. Okay, so you want x to be greater than 7.38. That's like, I mean, you could just say, take n to be 8, right? Then at least from that point forward, you're good. You're eventually decreasing. Your derivative is negative past the 8th term, which is good enough. Then you should also check your limit. So the limit looks like this. Natural log of n over square root of n. It takes a little bit of doing. This is another application of L'Hopital's rule. Derivative of the top is 1 over n. Derivative of the bottom is 1 over 2 square root of n. And what do we get? Simplifying this, that'll be 2 root n over n, but that's 2 over root n. And that's 0. So let me scoot this up a little. We've sort of run out of space. Okay, equals 0. So that implies, well, both of those two things, the fact that you're eventually decreasing and the series has limit 0, non-alternating term does. Then that implies together that you converge by the alternating series test. Okay, now we're getting into some crazy ones. Number 29 looks like an alternating series. But we have to be a little careful, right? So if you think, let's apply the alternating series test, you would want to check that cosine of 1 over n squared is decreasing. That'll probably be ugly. So let's start by checking the other one, right? Let's just check condition 2, that the limit of the non-alternating part is 0. Okay, well, cosine is a continuous function. 1 over n squared is continuous, at least for positive values of n. So I'm allowed to push the limit inside the cosine. And then limit as n goes to infinity of 1 over n squared is 0. So this is cosine of 0. Oh, but cosine of 0 is 1, right? Which is not what we wanted, right? Up above, we just did this one. We want the limit to be 0. The terms have to be approaching 0. If not, well, this is just as good as the divergence test, right? The divergence test says if your terms are not going to 0, then the series diverges. And I mean, sure, our series is actually a little different. It has an alternating component. But if the non-alternating component's going to 1, the alternating component's going 1, -1, 1, -1, 1, -1, that won't converge either, right? The limit won't exist there. So this is divergent by the divergence test. So we thought we were going to use alternating series, and we ended up using the divergence test, but there we go. So it's a good idea to start with condition 2 most of the time, because you might waste time checking if something's decreasing, but then, oh, the limit's not going to 0. So that's always faster. Okay, next one on the docket is number 31. 31 is a tricky one. It helps if you think, well, it helps if you think about the graph of the tangent function. So the tangent function looks something like this. Okay, that's y equals tangent of x. And we're plugging in values into the tangent function. We're plugging in 1 over n. So 1 over n is 1, a half, a third, a fourth, a fifth. And it's getting smaller, right? So the more terms you go out in your series, the smaller things you're plugging into tangent. And one really nice thing about the tangent function is, well, if you're plugging in small values, meaning, okay, you're close to 0, you're close to the origin, then tangent of x actually looks like x, or sorry, y equals x. It looks like a, okay, I didn't draw it perfectly, but imagine it's a diagonal line with slope 1. They look really close together at the origin. So that suggests that tangent of 1 over n, well, let's write this out. Tangent of x is basically x for small x. So tangent of 1 over n should be basically 1 over n for large n, right? Because if you're talking about small x, that means 1 over n is small, but 1 over n is small when n is big. So this is true for large n. And okay, maybe that's where I come up with my comparison, right? I'm thinking tangent of 1 over n is like 1 over n. 1 over n is the harmonic series. So maybe I expect tangent of 1 over n to diverge. And I can check that it actually does by doing a straight up limit comparison test. Tangent of 1 over n compared to 1 over n. Okay, and I don't need to simplify this algebraically. I can just take the limit, right? So the limit, if I think about the top, well, the top 1 over n is going to 0, and tangent of 0 is 0. So the top is going to 0. The bottom is also going to 0. So it's indeterminate form, 0 over 0. That lets me take a derivative of both. then focus on how fast one is growing relative to the other, right? Their derivatives. Derivative of tangent 1 over n is secant squared 1 over n. And then chain rule says multiply by derivative of the inside, so that's negative 1 over n squared. On the bottom, derivative of 1 over n, well, we just did that. That was negative 1 over n squared. So we get some cancellation here. And I'm just looking at the limit of secant squared 1 over n. But again, I can push that limit inside. So this is secant squared of the limit of 1 over n. But the limit of 1 over n as n gets big as 0. So this is secant squared of 0. Put that in parentheses. Secant is 1 over cosine. So this is 1 over cosine squared of 0. But cosine of 0 is 1. So this is 1. And that's good. That's a finite positive number. That means the two series you are comparing, so tangent of 1 over n and the harmonic series, behave the same. So that tells me that my series diverges. And that is by limit comparison. Cool. that one's pretty out there. Number 33 is probably not as bad. Yeah, so the thing to think of is, again, think of what the graph looks like, at least for the numerator. So the numerator, 4 minus cosine n, well, cosine of n looks like this. So negative cosine of n looks like a flipped version of that. This is negative cosine of, well, x, I guess. But then I'm adding 4 to that. So I'm shifting it up like real high. This is 4 minus cosine of x, way up here. This is 4. And so, okay, it's not alternating, right? That's definitely above the x-axis. The terms are positive. So, in fact, I mean, you could make the observation that it's always above 1. Here's 1, equals 1. The graph of 4 minus cosine x is bigger than 1. So, okay, make the observation. Let's scooch this somewhere else. So that observation tells us that 4 minus cosine n is always bigger than or equal to 1. Well, it's never equal. I guess I could write strictly greater than, but who cares? And so this whole series is strictly bigger than, just replace the numerator with 1. The denominator is n to the 1/2 power. And we know that that diverges by p-series, right? So we're bigger than a divergent series. That means we diverge, and I'll say this is by direct comparison to p-series. P-series with p less than or equal to 1. Okay. 35 then. 35 looks surprisingly, okay, it looks scary at first glance, but it's actually nice. And the reason is, and this is maybe just something you can remember, or maybe you see it enough that you get used to it, n factorial grows faster than e to the n or e to the n squared or anything to a power. N factorial is huge. So the numerator is blowing up. I expect this to diverge. And all I have to do to test that is the divergence test. I guess I don't want to do that because I don't know how to take a derivative of n factorial. I mean, I do, but you guys don't. So let's instead do something nicer. Let's say I want to do the ratio test, right? Because n factorial is really nice when you do the ratio test. So maybe that'll be better. So I look at my n plus first term. You might say this denominator looks ugly, but it'll work out. Don't worry. And then, okay, that's the reciprocal. Everything's positive, so the absolute value doesn't matter. And as always, our factorials mostly cancel. On top, n plus 1 factorial is n plus 1 times n factorial. So the n factorials cancel, and I'm just left with n plus 1. And then the remaining terms, well, let's actually FOIL this guy. So n plus 1 squared is n squared plus 2n plus 1. And then looky here, whoops, I meant to highlight. Those are the same, which is good to see. In fact, this, I mean, you can use rules of exponents and split it up into 2 exponentials. Instead of summing exponents, you can multiply them like that. So in fact, those cancel straight away. And you are just looking at the limit as n gets big. Okay, I have this n plus 1, and I have this e to the 2n plus 1 on the bottom. And okay, maybe that's, you know, an indeterminate form, and we have to use L'Hopital's rule. But I'm just going to wave my hands and say this is growing faster. So the denominator blows up, and this goes to 0. But feel free to use L'Hopital's rule. You get the same thing. 0 is less than 1, which implies, oh, that's fine. I was expecting this to diverge, wasn't I? Okay, well, that implies absolute convergence. So that implies convergence by ratio test. I guess sometimes intuition can fail you. But anyway, yeah, I guess it's coming from the fact that this is n squared in the exponent. So the bottom is blowing up faster than it would have been if it was just e to the n. Anyway, 37. 37's rough. 37's rough. What I want to say is you can probably get away with some comparisons because it looks complicated. And whenever you see a complicated series, you should try to compare to a simpler one. In particular, you could say this plus 1's annoying for sure. That makes the denominator bigger than if it were just k cubed, right? Which makes the whole fraction smaller. So I could at least start by saying, you know, whatever series I started with, the hideous series I started with, is going to be less than or equal to this series, right? Because the denominator on the left was bigger. So the whole fraction on the left is smaller. But okay, I have k over k cubed. So like one of those cancels. And it's really just, let's actually write it out. Log k over k squared. But that's still kind of ugly, right? I can't make it look any nicer. Like maybe you want it to be less than or equal to like 1 over k squared, but that's not true because natural log of k is not less than 1. So you can't go that far. Can't go much further at all with comparison. So the question now becomes, does this converge or diverge? The intuition is it probably converges because there's a k squared on bottom. So it's like almost like a p series, not exactly, but this log k isn't going to fight strong enough to make the numerator win. And so, okay, how do I show something like this is convergent? It's not alternating. I already said I can't do any comparison type stuff. Or can you? I mean, maybe you could do a limit comparison to 1 over k squared, right? You can't do a direct comparison, but why not try a limit comparison? Let me think if that would actually work. Because you would compare to 1 over k squared, that would cancel, the log would go to infinity, huh? Which is not ideal. So yeah, I think if I'm doing this correctly in my head, then I think limit comparison is not a great idea, because I think the limit of their ratio would be infinite. So are we out of luck, right? You can't do root test, you can't do ratio test. Or at least it wouldn't look nice if you tried. But when everything else fails, you should probably think integral test. So let's set f of x equal to log x over x squared. So the function version of the sum and there. And we should ask ourselves the usual three things. Is that a continuous function on our domain? Yeah, log is continuous. 1 over x squared is continuous as long as x is positive. Are the terms always positive? Again, yes. They're positive or they're 0, right? I mean, k could be 1, or x could be 1, and then log of 1 is 0, but that term is not going to impact us. And then past there, it is positive, so good. 3, is it decreasing? And that one maybe takes a little bit of work, right? You want to look at the derivative. A little longer. So I square the bottom, and then it's bottom times derivative of the top minus top times derivative of the bottom. And see if we can simplify this. That'll be x minus, yeah, it doesn't simplify much. It's just x minus 2x log x. But we can check if that's less than 0 to see if the derivative is negative. That's the same as, well, the bottom is always positive. So that's the same as saying the numerator has to be negative. Maybe we factor out this x. So this is now 1 minus 2 ln x. We want that to be less than 0. Again, x is always positive. So for a product to be negative, we need one of the components to be negative. In this case, the only option is that the second one, the one in parentheses, needs to be negative. But this is the same as saying 2 log x should be greater than 1, which is the same as saying log x should be greater than 1/2. And the question is that true? And the answer is yes, as long as you pick x big enough, right? You exponentiate both sides here, and that's the same as saying x should be greater than e to the 1/2, which is square root of e. And this is where we might stop and look up what square root of e is. E is 2.718, and if I square root that, I get 1.64 approximately. So okay, as long as I take x to be like 2 or bigger, then we're good. Okay, so technically I should start my series at 2, but it actually doesn't matter. I don't even have to wave my hands and say eventually decreasing in this case, because when k is 1, the first term is 0 anyway, so it's equivalent to starting at 2. So let's erase this. Right, we're good. You can go back in the video if you need to look at it. Basically, that just convinced me that not only is it eventually decreasing, it's like, yeah, it's always decreasing because our series might as well have started at 2. 2 is bigger than square root of e. Okay, so maybe that's a bit confusing, but let's forge ahead. So we're looking at the integral version of this. So we can apply the integral test. And you might say to yourself, this is almost ideal, right? I can almost do a u substitution with u as natural log of x, but it doesn't work because there's an x squared in the bottom, not just an x. But I could do maybe integration by parts. So maybe I try, same deal, pick u to be natural log, and dv will be the rest of it. Differentiate u to get 1 over x dx. Integrate dv to get v as, let's see, that's 1 over x squared is x to the negative 2, so that becomes x to the negative 1 over negative 1. That's negative 1 over x. And now we apply the formula. Let's first write this as a limit so it doesn't look like an improper integral anymore, and then I'll apply the formula. Natural log x over x squared dx. Okay, so formula says, I should put here, uv minus the integral of v du. So u times v is natural log of x times negative 1 over x. So that gives me negative natural log of x over x, I'll write it as. And I have to be cognizant of my limits. So this is 2 to t minus the integral of v du. But there's a minus sign on one of those, so I guess this becomes a plus. Integral from 2 to t. V du is just 1 over x squared. So write that as x to the negative 2. And let's do that integral. Let's leave this the same for now. I don't want to mess with it yet. The integral of x to the negative 2 is negative 1 over x. Okay. And now we can plug in our bounds. So I get, this is going to be sort of ugly, negative log of t over t minus a negative, so that's a plus, log 2 over 2, minus 1 over t minus a minus, so that's a plus 1 over 2. Anyway, the constants tend not to matter, right? We're taking a limit, so even if I'm off by a minus sign, it's not a big deal. In the limit, this guy goes to 0. And the only real question is what happens to this, negative log t over t. I mean, they're both numerator and denominator are going to infinity, so I need to be careful and do L'Hopital's rule, but that would get me 1 over t or negative 1 over t on the top, and that would go to 0. So both of these guys go to 0, and you're left with some finite thing. Right. Again, maybe I did my math wrong somewhere, and I missed a minus sign or something, but it doesn't really matter. What matters is that is a convergent thing. And so, yeah, so this converges, right? The integral converged, and we passed the 3 conditions of the integral test. So that means our series converges. I'll just write integral test. Okay, so that's usually, you usually don't want to do integral test unless you have to, but I think we had to there. 39 I'm skipping because it had hyperbolic cosine, and we're not going to worry about that. 41 looks interesting. It has a bunch of powers of k, and so you might think of like 2 things right off the bat. You might think, ooh, it's almost geometric, or you might think, ooh, I could do a root test, but neither quite work out, right? Because if you're thinking geometric series, you'd want to show that this is less than a geometric series. Which, well, less than a geometric series with a nice common ratio, and in this case it's not. And you know, if you thought of taking a kth root of everything, you're out of luck because the bottom won't simplify. So you probably just think, let's write out some terms. So for k equals 1, this would be 5 over 7. For k equals 2, it would be 25 over actually, it's 25 over 25, because 3 squared plus 4 squared is 5 squared. It's like a 3, 4, 5 triangle. When k is 3, this would be 125 over 3 cubed is 27, 4 cubed is 64, so that's 91 or something. It doesn't exactly matter. The trend you might observe here is this is less than 1, this is equal to 1, this is bigger than 1. And it's probably going to keep getting bigger. So you might think, oh, if the terms are getting bigger, I can just apply a divergence test. It's supposed to be a 4 to the k. So I just like look at the limit here. And then, yeah, this is going to infinity. I can't think of a nice way to convince you of that right now, other than saying 5 to the k grows faster than 4 to the k, right? And the 3 to the k is not going to matter. It's even smaller. So yeah, I guess technically all you really want to show is that 5 to the k is, well, yeah, it blows up much faster, right? You keep repeatedly multiplying by 5. That's gonna dominate. And so this implies you get divergence by the divergence test, because you got something other than 0. 43 looks intimidating, but don't be freaked out by n squared as a power. Still think, if that was an n, I would know what to do. I would do a root test. And so let's try the root test and see what happens. So we would be taking the nth root of the absolute value, and the absolute value is not going to matter, but I'll write it anyway, of our terms. Okay, and like I said, absolute value goes away. The nth power, right? I could write it like this, maybe. The nth power is just, or the nth root, sorry, is the 1 over nth power. So that would be just x to the n. So the 1 over n and the n squared sort of cancel. The absolute value goes away, and I just get n over n plus 1 to the n. And this might look semi-familiar. We have a little fact that I could bring up, that there's sort of a well-known limit. This guy, 1 plus 1 over n to the nth power. As n gets large, this goes to e. Sometimes this comes up in compound interest problems. But yeah, if you take that for granted, then great. There's an even better version, which is replace the 1 with any value you want. I'll call it x. Then that limit is e to the x. Okay, so if we know that, and maybe you didn't, but if we know that, we should be able to leverage the similarity between these two things. Right? They don't look exactly the same, but I'll try to make one look like the other, and then we'll be able to use it. So one way I could do that, I mean, I see here that it's not a single fraction, it's split apart. So how can I split apart this fraction? Well, I mean, I can't unless I do my little trick of adding 1 and subtracting 1 to the numerator. And then, okay, split it up into 2. The first is n plus 1 over itself, that's 1. Okay, and we're like, oh, that's good. I wanted a 1 to appear. And then the next one is like minus 1 over that denominator. So minus 1 over n plus 1. That's still at the end. And then we think, maybe that's not so good. Right, I wanted a plus, I got a minus, but I mean, I said x could be anything, so maybe x could be negative. Let's go ahead and take this minus sign and put it up on the numerator. So that's one step closer to being what I want. And I have 1 plus something raised to the nth power. The only thing that's really, the only discrepancy we have right now is these are not the same thing, whereas in the formula, they are the same. It doesn't matter if they're both n, I just want them to be the same. So could I make them the same? Yeah, I could, right? I could write this as, okay, this is gonna be wacky. I could force this to be the n plus first power. Of course, I mean, I can't, right? Because these two things are different, but I could make them the same if I then divided by the piece in parentheses. Right now, the fact that this is down here would kill that plus 1, and that does get me back to here, so that effectively doesn't change anything. And then I'm asking about the limit, and the limit on top is exactly what we wanted to see. right? And you might say, well, we wanted to see n and n. We're seeing n plus 1 and n plus 1. But it's the same deal. We're taking the limit as n gets big. So who cares if it's n or n plus 1? It's going to infinity either way. So the top is exactly what we want, right? And all the question is what's x? Well, x here is -1. So that limit should be e to the -1. But what's the limit on bottom? Well, -1 over n plus 1 goes to 0. So you just get 1 plus 0 on the bottom. 1. And okay, e to the -1, I could write it as 1 over e. And then the question is, what were we doing this whole time? We were doing root test. So is this a good value to get from root test? Yeah, I mean, 1 over e is like 1 over 2.7. So that's less than 1. That implies we converge. And we're done. Okay, so weird fact we had to use to be able to solve that, but there you go. 45 is even worse. 45, you look at it for a while and you're like, oh, that exponent's weird, 1 plus 1 over n. That's always positive, and in fact, 1 plus 1 over n is always bigger than 1. So maybe you think this is a p series with p bigger than 1, and you're like, oh, that's convergent, good to go. But, it's not. I mean, this power isn't fixed. It's not n to the 1.5. It's n to a variable power. And, if you get far enough out in this sequence, right, initially it's like, n to the second power, n to the 1 plus a half, n to the 1 plus a third. But eventually it's something stupid like 1 over n to the 1.000001. And you're like, man, that's really small. And like in the limit, maybe it's behaving like the harmonic series. Even though it looks like it should be a p series, like the exponents are getting smaller. And so if you think it's behaving like the harmonic series, maybe you think to do a limit comparison. Right? And let me actually make this look nicer before I do that. So you could rewrite the denominator as n times n to the 1 over n, which is the same as n times the nth root of n. Okay, so we look at the limit of that series over the harmonic series. And of course, multiplying by the reciprocal, we get that's n over n times nth root of n. But the n's cancel, so this is the limit as n gets large of 1 over the nth root of n. And then, again, you need a fact, which maybe you haven't seen before. The limit as n goes to infinity of the nth root of n is actually just 1. It's a weird fact, but but it's true. And so this limit is 1. And that's a good thing. That means that our two series behave the same, right? We were doing the limit comparison test. So our series behaves like the harmonic series, which means, our series diverges by limit comparison. Uh, 47 is the last one. 47 looks like, I mean, you might think you should do binomial expansion here, and I would say that's a good thought. But it's hideous, and it would give you a nested sum. You would get 2 sums within one of them. So instead, you probably want to say, oh, nth power, I should do the root test. So I take the nth root of everything. I take the absolute value as well, but these terms are positive, so it's not going to matter. Basically, the nth root goes away, or the nth power goes away, and I'm just looking at this. And then, again, you need a little fact. This is really similar to the one I wrote before. the nth root of 2, and maybe this one's more sensible, the nth root of 2 goes to 1. The square root of 2 is 1.4. The cube root is less than that. The fourth root is even less than that. But the limit in the long term is 1. Anyway, that means, okay, this goes to 1. So the whole limit goes to 1 minus 1, which is 0. And so by the root test, right, this is less than 1. By the root test, this converges absolutely, which means it converges. And we're done. Right, so that's everything. 3 pages worth. Took me about an hour or so. But there you go. I hope that was helpful. Don't be discouraged if you struggled on some of them. So did I. I had to prep this in advance because I made too many mistakes the first time. So yeah, there it is. I hope it helped, and good luck with your study.